Hi, this is Professor Fernandez. We're talking here about video 1 in lesson 8. This is the topic of instantaneous speed. So I'm going to go through this applied example 3.3 from Calculus Simplified. So instantaneous speed, like we talked about in the text, is pretty neat concept. If you have an object that is in motion, right, you can imagine freezing time and taking a snapshot. So you might have like a photograph of a ball that's, a basketball, let's say, that's in the air, or tennis ball. And you might freeze time and you might wonder, what is the speed at that instant? How fast was it moving at that instant? That's instantaneous speed. For all the reasons that we talked about in Calculus Simplified at the beginning of Chapter 3, there's a really, really nice way that calculus approaches this problem, and that's using limits. So this is the definition down here that I'm just going to review very quickly. It says the instantaneous speed at time t equals a of an object with a certain distance function, we denote this by the script s of a, is defined by this thing. So a couple of things to point out here. First of all, this definition requires a distance function, right? So speed is kind of like velocity, except we don't care about direction. But its speed is a rate of change. It's a change in position or a change in distance, right, over time. So I really need some information about the distance that the object has traveled. And this is encoded in the distance function. If I know the distance function, then this definition tells me that I have to calculate this quotient and then find the limit. And if the limit exists, then that will be my instantaneous speed. For any real world distance function, the limit will exist. Objects in the real world, where we model them with distance functions, have speeds. So there's no worry that the limit won't exist for a real world object. So let's go back to the applied example. It says calculate S of A for the falling apple's distance function. You might be wondering, what is the falling apple? How did that make its way in here? In the beginning of chapter 3, I used the example of an apple falling to the ground to motivate this concept of instantaneous speed. So that's where the context comes from. But all we need, truth be told, is this distance function. So what I'm going to do now is calculate this difference quotient. That's what the difference of the numerator divided by delta t is called. And then I'm going to go ahead and find the limits and then see if we get something that we can make sense of. Great. So the first part is d of a plus delta t minus d of a divided by delta t. Right. So again, I'm calculating this thing that's circled over here. Now this is really a function composition problem. So d of a plus delta t is, I'm going to go over to t here and understand first what the function is doing to t. It's squaring it, multiplying it by 16, okay? And then everywhere I see a t, I'm going to substitute a plus delta t. So there's the t. So a plus delta t is going to get squared multiplied by 16. That is the function, right, d of t. Great. And then this over here says, how about I write over the same function, except instead of putting a t there it is, I will put an a. So this would be minus 16a squared. And then the denominator is delta t. Delta t, by the way, is the change in time, right? So what's really going on here, this was in the beginning in chapter 3, but what's really going on here is that this is the change in distance between time t equals a and t equals a plus some other time, right? You'd think of delta t as a small, maybe 0.1 seconds or something. So this numerator here is the difference in distances between those two times, divided by the difference between those two times. That's why it's literally a speed. It's an average speed specifically. So we're calculating here the average speed. And then let's go ahead and do some of the simplifications. I'm going to square this out. So first thing I do, you can think about it this way, or you can remember how you square things using the expression that comes from x plus a squared, which is x squared plus 2ax plus a squared. Either way you do it, you will get 16 times a squared plus 2 times a times delta t plus delta t plus delta t squared. All right. So I'm kind of using this one here, but we would have gotten the same thing if we FOILed this out this way. All right. And then the denominator is still delta t, so nothing changes there. Next, I will distribute the 16 to each one of these terms. So I get 16a squared plus 16 times 2, 32a delta t. And then 16 times delta t squared. Okay. And then I'm still subtracting a 16a squared divided by delta t. Okay, now I get to step back and see if anything cancels. That's one of the telltale signs in a math problem that you might be going the right direction. So indeed, the 16a squareds cancel, and I'm left with 32a delta t plus 16 delta t squared divided by delta t. I can factor a delta t from the numerator. So let's see where we can move it. Let's move it over here. Factor a delta t from the numerator. What am I left with? Factoring delta t out of here leaves me with 32a. Factoring it out of here leaves me with 16 times delta t divided by delta t. Okay, so here I can then cancel my delta t's. All right, same caveat that I've made in previous videos. Delta t is a change in time. We don't want the change in time to be 0 because that would have meant dividing by 0, which we can't do. So in this cancellation, I want to keep that in mind, that I can cancel so long as delta t is not 0. And that's totally okay, because if we go back to the original definition of instantaneous speed, I am taking the limit as delta t goes to 0. Okay, so delta t is not becoming 0, right? Limits approach indefinitely but never arrive. So I'm okay in okay shape to claim that for our purposes, right, this quotient simplifies to that, which does not have a denominator of delta t anymore. Great, so if I were to summarize what we have just done and clean things up a little bit, we have found that d of a plus delta t minus d of a divided by delta t equals 32a plus 16 delta t. And again, we're assuming delta t is not 0, which it isn't because we're taking the limit. So now we're going to take the limit. So the limit as delta t goes to 0 of this expression is the same as the limit of delta t as delta t goes to 0 of this expression. Great. And then now we're kind of back to the limit laws that we learned from chapter 2. Think of, it can be a little confusing, but think of delta t as one thing, almost as if it were like x. Okay. So if I take the limit as delta t goes to 0 of this first term, it doesn't have any delta t's, right? So it stays what it is. If I take the limit as delta t goes to 0 of this next term, this one does have a delta t. It's right there, and it's being multiplied by 16. So I'm thinking about 16 multiplying something, delta t, that is going to 0. So that's going to go to 16 times 0. Okay, so my final answer here is 32a. I've calculated this limit. I have arrived at an expression. Nothing has gone wrong mathematically, no division by 0, no negatives under the square roots, nothing of that sort. So this is my instantaneous speed, right? S of a equals 32a. Where did I get the S of a? Well, that's just a notation that we used, denoted by, for the instantaneous speed, right? The outcome of the limit. Okay, what does this mean, right? We've done the math. Let's talk very briefly about the physics. This means that if I imagine an apple, I'm going to try to draw an apple as best I can. It's a terrible apple. There's my apple. If I imagine an apple that is falling, okay, and it has been falling for some time, and then I freeze the motion at time t equals a, right? There maybe is a stopwatch. Maybe there was a tree up here. I feel like my 5-year-old now. Maybe there was a tree that the apple fell out of. And as soon as it fell, I started my stopwatch. And then t equals a seconds later, I want to find out how fast the apple is falling. What is the instantaneous speed? Assuming, of course, it's still falling. Then this is the answer, 32a. So if the apple was still falling 1 second after it fell from the tree, then the math we've just done shows that its speed would be 32 in whatever units we're using. 32 feet per second squared or 32 meters per second squared, whatever the units you're using are. Great, so that is how you calculate the instantaneous speed for an object whose distance function is 16t squared.